Everybody looking forward to this afternoon? Yeah. We got a little bit of math to do today. Probably 20, 30 minutes of stuff that I want to talk about, and then I'm going to be done. You guys think we can swing that? Yeah, I think so. Okay, so today what we're going to start by talking about is how to find mins and maxes, and then as a result the range for these polar functions. So we'll just start with a maximum question. So say we want the maximum value for r in the equation r equals 3 plus cosine theta. So what part of the equation r equals 3 plus cosine theta is going to dictate the maximum size for r? What's the only part that's variable? The cosine theta part, right? Right? If I'm talking about the maximum value for r, 3 is constant. So the only part that I really need to be concerning myself with is that cosine theta part. Who remembers the range for cosine theta? It's a first semester question. Carmen?
Is it 0, 1?
Okay. The 1 is the maximum value for cosine. 0 is not the minimum, though. -1 is the minimum. Yep. And that's the same for sine and cosine. So here, if we're looking for the maximum value for r, we also want the maximum value for cosine. Everybody agree with that? So that we can say the maximum value there is just going to be 4. You guys Stucoing things? Okay. No problem. Okay. Let's do a range question then. So let's say we were interested in the range of r in the equation r equals 4 minus 3 sine theta. So again, which part of r is the variable part? The sine theta, right? So we're going to be concerned with the outputs for sine theta. Those outputs would be the range for sine theta, -1 to 1, just like cosine. So we know that one maximum or minimum is going to occur when r equals -1, or when sine is -1. And then the other extrema is going to occur when r equals +1. So if I do that, I get 7. And I do this one, I get 1. So the range for r would be 1 to 7. Feels pretty straightforward. Yeah, I think so too. The next thing we're going to talk about is symmetries in these polar functions. So if you remember way back in first semester, there was 3 types of symmetries we talked about. Right? We have symmetry with respect to the x-axis, symmetry with respect to the y-axis, and then that like rotational symmetry, right? So the same thing is going to exist here. So we have 3 types of symmetry: x-axis, y-axis, and alpha point symmetry. So to prove that we have x-axis symmetry, we replace r and theta with r and negative theta and show that we get the original equation back again. If we want to do y-axis, we're going to replace the r and theta with negative r and negative theta and see if we get the original back again. And if we think we have alpha point, we're going to place r and theta with r and theta plus alpha and see if we can get the original to come back again. So the way these would be phrased, or these kinds of questions will be phrased, will be like, prove that the function has the following symmetries. So let's start by doing y-axis. So we have the function r equals 5 sine 3 theta. So if I want to do y-axis symmetry, what am I trading out? My r and theta are going to become negative r, and theta is going to become negative theta. And now I want to try to simplify this equation down so that I end up with what I started with. Okay, well, I know that 3 times negative theta is just negative 3 theta. Everybody's okay there? And if you think back to first semester, we have an identity for sine of negative theta. Everybody remember that? What is that? What is sine of negative theta equal to? Carmen?
Negative sine times theta?
Excellent. Yes. So that's going to turn into negative sine of theta. And if we divide both sides by a negative, we're back at the start, which is what we wanted to have happen. So we're done. Everybody okay on that one? Questions on any of that? Okay. So here we have 120 degree point symmetry. So I'm going to be replacing r and theta with r and theta plus 120 degrees in this case. Still okay? So I'm going to go ahead and distribute the 3. Still doing okay? Now I have sine of 3 theta plus 360. What can I do with that? No. Remember, we have these angle sum and difference identities. So that's what I'm going to use. Okay, so cosine of 360 is just a number, right? Who remembers what cosine of 360 is? It's going to be a unit circle question, right? It is 1. And sine of 360, again, is just a number. Sine of 360 is 0. And I know that 0 times anything is just 0. So that stuff just cancels out. And surprise, surprise, we're left back with what we started, which is what we were trying to get to. Everybody's okay with this? Okay. So that's how we kind of prove these different types of symmetries with a polar function. What I want to do now is talk about 2 different kinds of polar functions. So one is called a rose curve. So a rose curve is something that's of the form r equals a times cosine n theta, or r equals a times sine n theta, where n is greater than 1. So this last function we just looked at, r equals 5 sine 3 theta, is a rose curve, right? That fits the definition here. Let's just take a quick peek at what that's going to look like. So I'm going to pull out my calculator, pop it into polar mode. We'll do 5 sine 3 theta. And just take a quick peek at my window. That seems appropriate. Look what we get. Kind of looks like a flower, doesn't it? That's why we're calling this a rose curve. So the domain for rose curve, well, theta is going to just be the domain for sine or cosine, which is all real numbers. The range, well, if it's just a times sine or cosine, it's just going to be negative the absolute value of a, positive absolute value of a for our range, because the range of cosine and sine are both -1 to +1. The maximum value is just going to be the absolute value of a. The number of petals, so here you see 3 petals on our flower, is the same as the coefficient on our theta. And then depending on the type of n and whether you have sine or cosine, we can determine our symmetry immediately without having to do any proof. So if n is even, then we have all three types of symmetry. Notice that this one has y-axis symmetry, but it doesn't have x-axis symmetry. If we had changed this to, say, 5 sine 4 theta, here we have both x and y symmetries. Everybody's okay with that? And we also have rotational symmetry. If I spin this, like some number of degrees, it's going to be the same picture, right? All I have to do is spin it like 1 petal degree. You kind of see that? And then likewise, if n is odd and we have cosine, it's an x end alpha point. If n is odd and we have a sine, we have y end alpha point. Go away. So let's say we're asked to analyze the graph of this function. Well, let's just take a quick peek at it, right? That'll be fun. -6 cosine 5 theta. Take a quick peek at it. Ooh, pretty. All right. So what can we say here? Do this so I can look at that at the same time. Okay. What's the domain going to be? It's a rose curve, so I know it's always all real numbers. What's the range going to be? It's going to be -6 to 6. So far, so good. What's the maximum value? Well, obviously 6, right? It's the top of the range. How many petals should we have? 5, which matches what I see in my picture, right? And then the symmetries. What kind of symmetry do I have here? Well, I have n is odd, and I have a cosine function. So I should have y-axis and alpha point. What is the alpha point, though? What is the alpha? How am I going to find that alpha? Well, clearly, if I spin this 360 degrees, I get the same thing I started with, right? So how much of 360 is it going to be from this petal to that petal? Should be 1/5, because there's 5 petals, right? So alpha should be 360 divided by 5. So it should be 72 degrees. What do you guys think? Basically just using the properties, right? No big deal. All right. The other type that we have is called a Limousin curve. So that that weird little C with the tail on it. Spanish people, what's that thing called where we have a C with a tail? Is that a Spanish letter or is that some other language's letter? It's not a Spanish letter? Okay, that shows how much I know about stuff. Anyways, I don't know what that thing is called where you have the little tail on it. Okay, so again, this is where we have some constant plus or minus b cosine theta or b sine theta. Notice that the requirement is both a and b have to be considered positive. Now you can still have a subtraction symbol in front of b, but when we fill this stuff out, we're assuming b is a positive number, even if it's like 3 minus 5 cosine. A is 3, b is 5. And if it was a plus 5 cosine, a is 3, b is still 5. Everybody's okay with that? Okay, so the domain, still all real numbers, not surprising since the domain of sine and cosine was all real numbers anyways. The range is going to be a minus b and then a plus b. Again, since a and b are both positive values, we don't have to worry about absolute values or anything in there. The maximum value for r is going to be just a plus b, shocking. And then the ratio of a to b is going to tell us about the shape of our Limousin curve. So let's just look at a couple of examples here real quick so you can see what we mean by inner loop and cardioid and dimpled and convex and all this jazz. All right, so a over b has to be less than 1. So maybe we do that, where a is 2 and b is 3. So 2 divided by 3 is less than 1. This should be a inner loop. Let's do this. Oops. I'm going to turn the axis off real quick so it'll be a little bit easier to see the features. So see the little loop on the inside? That's why we call it an inner loop. Let's now make them equal. So that'll just make it 3 and 3. So cardioid kind of looks like a heart or maybe a butt. Cardioid, though, is like heart, is the root word there. If I have something between, a over b is between 1 and 2, so maybe I'll make a3 and b2. That'll be 1.5, so that'll be in there. So that's the dimpled. I think if we zoomed in real close here, you'd see like a little indent or something. The cardioid and the dimpled are the two that are the hardest to tell just by looking at the picture apart. And then greater than or equal to 2. So we'll make A4 and B, let's just make it A5 and B2 and see what we get. That's convex, right? Because that's a convex shape. There's no indent to it anywhere. Everybody's okay? So that's just some pictures to get an idea of what they look like. So let's do an example where we do the same thing that we just did, where we ask you to analyze the curve. And then we'll be done for today, guys. That's pretty good, right? All right. So I would start by just noting that A here is 4 and B is 3. And this is clearly a Limousin. Okay. So the domain, well, the domain is always all real numbers. That's easy enough. The range is going to be A minus B, so that's 1. And then A plus B, that's 7. And the maximum value is just clearly going to be 7 because it's the top of the range. If I look at this, A over B is between 1 and 2. So that tells me this was the dimpled. Put some commas or something in here. And the last thing I want to do is the symmetry. So this is the sine one. So we have y-axis symmetry. And I guess let's take a quick peek at what this guy would have looked like here. So 4 minus 3 sine theta. Oh, there's my dimple. See it right up there? And that's all she wrote, folks. So I think at this point we should be able to finish her out. So 85 to 96. That won't be due till next Sunday, though. So what's next Sunday? What is that? It's dates are hard, guys. Is it like 17 plus the date now? 26th. 10 plus the date now. That would have been, all right, whatever. For this weekend, though, that is 3 days later, right? Yes, good. Okay, what do we have due this weekend? Who remembers? I gotta look it up. So we'll say 49 to 62 is what we assigned so far, right? Have I not assigned 63 to... We should have done that last time, 63 to 84. When do you want that due, this weekend or next weekend? You want to just kick the can all the way to next weekend? That's fine with me. Don't cost me nothing, right? Don't say I didn't do anything for you ever. That's fine. Everybody happy? All right. So next, that was the last section in chapter 10. So next class we'll do the review day and we'll have the test the following. So test next week, some point. But that's a next week problem, not a today problem, right? Well, I am done with you guys. So I'm going to stop.